Hey everybody, this one is 4A work. So the scenario is, starting from rest, a 1 kilogram cart moves to the right along a horizontal surface that exerts negligible friction when being pushed by a horizontal force F as shown. The force exerted on the cart as a function of displacement is graphed below. So it's not versus time, it's versus displacement there. So we're going to use this graph here to answer the questions on this part right here. It says, claim the cart will have a change in mechanical energy of 48 joules as its displacement is changed by 12 meters. So we're going to collect that evidence here by looking at the area under the line of the force versus displacement graph is equal to. Well, let's look at that. To get the area, and by the way, we're only going to look up to 12 meters, so we're going to only look up to this spot right here. So we're going to go find the area underneath this line here. So to get the area, we'll do length times width. So our force here we can see is 4 newtons. So I'm going to write that here. The number is 4 and the unit is newtons. And then we're going to multiply that by our length here is in displacement. So it is going to be 12 by meters there. So 12 meters is the unit there. So when we go to multiply these two out, 4 by 12 is 48, and newtons times meters, newton meters, that gives us a unit of joules actually. So the area is also then known as the work done on it. So when you have a force versus displacement graph, the area under the curve, since it's force times distance, is equal to the work done on it. So this claim makes sense because the work done on a cart is also equal to the change in energy of the cart. So remember, when you do work on something, you transfer energy into or out of it there. So next part here, they explain how the graph above could be used to determine the speed of the cart after the cart has gone 12 meters there. Well, we know that the speed, if we change the energy, in other words, the amount of work that we did, is equal to 48 joules. Sorry, this marker is dying. Then we know that we gave that 48 joules of kinetic energy. So then we could set that 48 joules equal to the kinetic energy equation, which is 1/2 mv squared. And so we could solve for the velocity. They don't ask you to do that, but let's go ahead and do that real quick here. So we got 48 joules of kinetic energy now, and that will equal 1/2 times the mass, which is 1 kilogram, and we got to solve for the velocity squared. So divide this by each side by 1/2, divide each side by 1, we get 96 is equal to v squared. So square root of 96 is about 9.8 roughly meters per second. So next part here, they say on the graph to the right or below in this case, sketch a graph of the acceleration of the cart as a function of displacement here. So if we go back to this graph right here, we can see, and they only want us to do it up to 12 meters. So up to 12 meters, we had a constant force. So we are going to have a constant acceleration because acceleration is equal to force divided by mass. Our force was 4 newtons, our mass is 1 kilogram, so our acceleration is going to be a constant value of 4 meters per second squared. And again, we can end it at the 12 meters there. So next part, they say, after creating her graph of acceleration versus displacement, Angela says, oh, the slope of a velocity graph represents the acceleration. So since the acceleration is constant at 4 meters per second squared, the velocity should be aligned with a slope of 4 meters per second squared. I actually think this question is kind of confusing because it's not clear yet unless you look down below that this velocity graph she's talking about is this velocity versus displacement graph here. So what she is saying here is not true. At first you might think it's true because what she is talking about is a velocity versus time graph. Then the slope of a graph like that would equal the acceleration. And so the slope of a velocity versus time graph would be 4 meters per second squared. But what you have beneath there is a velocity versus displacement graph. And again, I think if you're just reading that through and you don't look down here at the actual velocity graph, it's not clear that that answer would be incorrect. But it is a velocity versus displacement graph, and they say they want you to plot it here. Well, let's look at it like this. How are we going to do this graph? Well, let's use what we called the first equation. Final velocity is equal to initial velocity plus acceleration times time. Let's assume this thing starts from rest, and therefore our velocity is just simply equal to acceleration times time. Or in our particular case, our acceleration is 4, so 4 times t. The other equation that we can use is the third equation. Our position will be equal to v0 times t, but no initial velocity, so that will drop out, plus 1/2 at squared. So if we substitute in for our a here again, we get 1/2 times 4 times t squared. And now we can start to plug in some points here and plot the shape of this graph. So for example, I'll go ahead and put in at 0 meters, we have 0 velocity. But then let's put in at 1 second here. At 1 second, 1 times 4 is 4, so we're at a velocity of 4. But where are we? So plug in 1 here. 1 squared is 1, times 4 is 4, half of that is 2. So we're 2 meters out when we're going 4 meters per second. So our next point should be right there. You can plug in now 1.5 seconds. And if you plug in 1.5 seconds, then 1.5 times 4 is 6, so we'll get 6 as our velocity, but put 1.5 in there and square it, and then multiply that by 4 and then by 1/2, and you will get 4.5. So when we are going 6 meters per second, we are 4.5 meters away. Let's do it now for 2 seconds. 2 times 4 is 8, so after 2 seconds we'll be going 8 meters per second. 2 squared is 4, 4 times 4 is 16, half of that is 8. So we'll be going 8 meters per second and we'll be 8 meters away. So we'll be right here. And if you repeat it again for 2.5 seconds, you will get that we are going 10 meters per second and that we're 12.5 meters away, so just off of here. So we're about right there. So you get this shape of a graph like that. And then the last part of this question here says the equation v squared equals v0 squared plus 2a delta x, what we called the fifth equation, can help describe the velocity of an object with a constant acceleration as a function of position. Is this equation consistent with your graph? Well, let's look at this. Again, no initial velocity there, so v squared is equal to 2a delta x. Well, let's solve for v. v is equal to the square root then of 2a delta x. The 2 is obviously a constant, the a is a constant, so we can write this. The velocity is proportional to the change in displacement. In other words, a velocity versus position graph should look like a square root function, which it does there.